Hi, welcome back to 345 Delta Foxtrot. This video is about a little experiment I did optimizing the shop head of rivets. In the last video, I talked about a little apparatus I put together to measure the strength of rivets. And so I made some different samples, and we're going to talk about the measurements and how they came out. So the experiment is very simple. You just squeeze rivets by different amounts, and then you measure how strong they are. First, very quick review here. You can have the forces on rivets can be either shear stress or tensile stress. If you're pulling the two pieces of metal sideways, as shown in the picture here, that's shear stress. And if you're pulling them apart, then that's tensile stress. And this is the notation that I use. The length of the rivet before it's squeezed is H. The diameter of the rivet after it's squeezed is W. And the thickness of the rivet after it's squeezed is T. All the rivets for this experiment were flathead rivets, not as shown in the picture to the right. Those are obviously roundhead rivets, but it was too much trouble to make a new picture. So they were 426 AD 3-4.5s, and H was almost exactly 1.5 D, which is considered the nominal or optimal value. That's the value that your rivet gauge from Cleveland Aircraft Tools has on it. Since they're flathead rivets, the top aluminum was countersunk. Okay, the aluminum for this experiment was a 16th inch thick 6063-T5 alloy aluminum. So a 16th inch is 62.5 thousandths, and a Van's skin is about 16 thousandths. So this aluminum is about 4 times thicker than a Van's skin. So that's intentional. That's so that we can look at the failure of the rivet itself in this experiment and take the skin out of the picture. And as already mentioned, since it was a flathead rivet, the top piece of metal was countersunk, and H was almost exactly 1.5 D. Okay, this is the experiment. Did 6 samples in tensile stress and 1 sample in shear stress. I started out with the squeezer set to the full length of the rivet. And that's what I call 0 turns. And so the first sample was, I tightened or made the gap smaller by 2 turns, and each turn is 1/32 of an inch. And if you try and go less than 2 turns, the rivet will fall out. There's a fairly abrupt transition here between the rivet falling out at 1.5 turns and maybe even 1 3/4 turns, and then the rivet staying in place at 2 turns. And then squeezed the samples more and more all the way up to 7 turns. So it spanned from 7 turns to 2 turns. So the span is 5 turns, and each turn is 1/32 of an inch. So I thought that was quite a lot. And then the sample for shear stress was 4.5 turns. So after I squeezed the rivets, I measured W and T, the diameter of the shop head and the thickness of the shop head. And those values are given here in inches. That's the first 2 columns in yellow. And then you just convert that to something times D, where D is 3/32 of an inch, which is the diameter of the rivets I was using. And so W is between 1.09 times D and 1.82 times D. And kind of the nominal value for W, for example, the value on the rivet tool that Cleveland Aircraft Tools sells, the diameter of the hole in the measurement tool is 1.5 times D. So sample number 4 is almost exactly nominal. And also sample number 7 is almost exactly nominal. Okay, here's the results shown in the column in yellow. And the first sample failed at 125 pounds. And as I already mentioned, it's a fairly abrupt transition. It goes from a strength of 0 pounds to a strength of somewhere around 100 pounds very quickly. In this case, it was 2 turns of the squeezer brought it to 125 pounds. And then you go just another half turn on the squeezer, and that takes it from 125 to 192 pounds. So the strength is increasing pretty rapidly. And then for the last 3 samples, they're all about the same, and they're all about 280 pounds. And the sample for shear stress was even higher, and it was up around 328 pounds. So this is how they failed. The first 3 samples, the shop head failed, and for the last 3 samples, the factory head failed. So there was a transition from how things failed right around nominal, right around 1.5 times D. If you squeeze it less than that, W is not big enough, and the rivet just pulls through the hole. And if you squeeze it more than that, then the shop head is actually stronger than the factory head, and the factory head is what pulls through the hole. And I didn't go far enough to see, to squeeze so much that the strength of the rivet starts going down again. I thought I was squeezing quite a bit, 7 turns of the squeezer, and the rivets, well, they were at 1.82 times D. I thought they were obviously over-squeezed, and that you know, I would probably see some reduction in the strength of the rivet, but I didn't. So as far as I can tell, it's very difficult to over-squeeze a rivet. And then the sample and shear stress, the rivet was actually sheared in half, just kind of a clean break right through the rivet. And that failed at about 328 pounds. Okay, these are pictures of how the samples failed, how they came out. And this is sample number 1. And the 2 pictures on top are they're the outside when the rivet was mounted up in the apparatus for testing. Those are the 2 outside surfaces, the top and the bottom. And the 2 pictures on the bottom here, those are the inside surfaces. Those 2 surfaces were flush up against each other when the rivet was being tested. So they're the middle or the inside surfaces. And so in the upper left, you can see the factory head of the rivet, and it's just fine. And then in the lower left, you can see the shop head and how it just pulled right through the hole. And then sample number 2 is very similar. The factory head in the upper left is just fine. The shop head in the lower left just pulled through the hole. It just wasn't squeezed enough. Sample number 3 is very similar. Shop head is fine, and I'm sorry, the factory head is fine in the upper left, and the shop head in the lower left just pulled through the hole. Okay, there's a big change here for sample number 4. In this one, the factory head failed. The shop head in the upper right is just fine. And then in the lower right, you can see what remains of the factory head, and it pulled through the hole, and the outer part of the factory head, the cone-shaped part, just pulled through the hole and is basically gone. Okay, sample number 5 is the same. The shop head is shown in the upper right. It's just fine. And then the factory head in the lower right, the outer part of the factory head just got sheared off, and basically the shaft of the rivet separated from the outer part of the cone of the rivet head. And it's more obvious in the next sample, but samples 5 and 6 basically failed the same way. So this is sample number 6, and you can see in the upper left picture, just below the sample, that's the cone of the rim of the rivet of the factory head. And so the shaft of the rivet just pulled away from the rim of the rivet, and in the lower right is what remains of the shaft of the rivet. And then the shop head is in the upper right, and it's just fine. Okay, this is the sample that was under shear stress, and you can see the factory head at the upper left is basically okay. And then below the sample in the upper right, that's what remains of the shop head. And you can see how the shaft of the rivet basically just sheared in half. And then in the lower left, you can kind of see the other half of the rivet and how it sheared in half. Okay, so what did we learn from this experiment? Well, the first thing we learned was that you want the shop head to be between about 1.4 times D and 1.8 times D. We didn't really have a sample at 1.4 times D, but we had a sample at somewhere around 1.2 times D, and it was pretty much okay. You probably want to go a little bit more than that. So somewhere around 1.3 to 1.4 times D is probably okay. And then, as far as I can tell, you can go almost as much as you want. It's hard to over squeeze a rivet, and went up to 1.8 times D and didn't see any problems. So I already went over point number 2. It's hard to over squeeze rivets. Third thing we learned is that the apparatus is capable of giving surprisingly consistent results. The last 3 samples, number 4, 5, and 6, they all failed at almost exactly the same amount, right around 280 pounds. Very surprising. Now, these rivets were probably all out of the same batch and all of that, and if if you took rivets from different batches and things like that, you'd probably get some variation here. And the rivets were surprisingly strong. A properly set rivet fails at about 280 pounds, which is much higher than I was expecting. Now, this experiment is looking at the optimum case where the rivet is what's failing, and this is not the actual use case. Don't expect the skins of your Van's airplane to be riveted this strong. And that's the topic for subsequent experiments. If you use more realistic settings where the thickness of the metal is somewhere around 16 thousandths, it's the typical Van's alloy and thickness for the skins. And also, any variation in the size of the hole or the position of the hole could affect the outcome substantially. Okay, that's pretty much it for this video. If you like these videos and you want to recommend them to other people with similar interests, then subscribe, give them a thumbs up, and or leave a comment. all those things will cause the YouTube algorithm to recommend these videos to other people with similar interests. And I'll leave links in the description for my previous videos about rivets. I think that's all the links for this video. So that's it. Thanks for watching.